subset, the positive integers, has a least element. Okay, sounds good. It fits with our intuition. Any finite set of positive integers, there must be a least one. Okay, because you just check the integers from 1 up. Is 1 an element of the set? Well, if it is, it has to be the least positive integer in the set. If it's not, check 2. If it's not, check 3. If it's not, check 4. Eventually, you'll hit the first element in the subset, and that's going to be the least element in that set of integers. So you can see there what the connection with induction is. Checking 1 in the set, checking 2, checking 3. That counting up to all the integers, that's the principle of induction, really. So induction and well-orderedness, they're two equivalent principles. And we introduced well-orderedness because it's a nice way of phrasing the principle of induction, and it's a nice way of approaching lots of proofs. And we saw it last time for this term. This characterized the greatest common divisor. Okay, so you can say the greatest common divisor. You can use the original definition, but another way of approaching it is saying that it's the least positive linear combination of the two numbers. Okay, this is what we proved in Theorem 2.3. And if you look at, given the common divisor D of A and B, the greatest common divisor, you can find coefficients M and N that express D as a linear combination of A and B. Linear combination of A and B. And in fact, it will be the smallest positive such linear combination. That would be the greatest common divisor. Okay. So we're going to go on to discuss this morning. There's a bunch of exercises there, which we may turn to a few of those now, and they'll be in play for the tutorials next week. But I want to introduce you now to the Euclidean algorithm. The Euclidean algorithm is a very famous result in number theory, and this allows you to find, it's an algorithm, it's a calculation technique, if you like, for finding the greatest common divisor of a given pair of numbers. And it can also produce the linear combination referred to in Theorem 2.3. So as well as finding D, the greatest common divisor of the two numbers, you can also produce a pair of coefficients M and N that give you a linear combination of the two numbers equal to D. Okay. So it's best to explore this by looking at a definition. Looking at an example. I haven't had my coffee this morning, so I'm a bit out with. Okay, so we're going to just have a look at example 2.2 here. Consider that. Try and get this on the camera. It's all possible. See if that comes out. Okay, so here we're tasking ourselves with finding the greatest common divisor of 525 and 19. This is example 2.2. Now, when we discussed the greatest common divisor, we did already talk about it in terms of how you might find it from the prime factorizations of both of the numbers. Okay? Because I got a good answer from the class there that the greatest common divisor of these two numbers will just be the overlap in their prime factorizations. Okay? You factor 525 into a product of primes, factor 90 into a product of primes, and then look at what's common from the intersection of the two factorizations is, that will be the greatest common divisor. Okay? But we'll come to see that, I don't know how to get rid of that silly menu. We'll come to see anyway that finding prime factorizations isn't an easy problem. Okay, so we'd like to have a way of doing it. We'd like to have a way of finding the greatest common divisors that doesn't rely on that. Okay. And one thing we also introduced last time was the notion of integer division with remainder. So yeah, I think it's the autofocus that kind of zips in and out. My hands are there. Sorry. I can't even see what's on the screen because it's spilling off the fabric.
I know I integrated 90. What did that say?
Sorry?
What did that say?
Consider integer, well, I didn't get all the way through that word, integer division. Consider integer division with remainder. See, if it was the case that 525 was something times 90, if it was the case that 90 divided 525, then the greatest common divisor, we'd recognize it immediately, wouldn't we? The greatest common divisor would have to be 90. 90 divides itself. If it was true that 525 was a multiple of 90, then 90 would be the greatest common divisor. We'd be able to recognize that immediately. But of course, 90 does not divide evenly into 525, but you can get 5 times 90 and then a remainder of 75. 5 times 90 is 450, yeah, remainder 75. So this is the process of integer division with remainder, 525 and 90. Okay.
Is it possible to have negative or min?
No, because when we set up the process of integer division with remainder, we divided a number a by a number b, and the property that the remainder had was that we always considered the smallest positive remainder you can have. So the remainder r will always be positive and strictly less than the absolute value of b. Okay. But if it was the case that we had a 0 remainder there, then this would show that the 90 divided 525, and therefore the greatest common divisor would have to be 90. But when we look at this, we notice that this expresses 75 as a linear combination of 525 and 90. So 75 is 525 minus 5 times 90. So we have 75 as a linear combination of 525 and 90. Now we're setting out to find the greatest common divisor of 525 and 90. So whatever it is, what can you say about the greatest common divisor of 525 and 90 from this equation? What other property does the greatest common divisor of 525 and 90 have? Or indeed any common divisor of 525? How do they relate to 75? Well, they divide it, okay? If you have any common divisor of 525 and 90, any integer that is a factor of 525 and it's also a factor of 90, we can see from this that it has to be a factor of 75. Okay? This was by theorem 2.1, part 3. Any common divisor of a pair of numbers also divides any linear combination of the two. So here's 75 expressed as a linear combination of 525 and 90. So any common divisor of 525 and 90 will divide 75. So let's say we're looking for, let's call the greatest common divisor D. So now we know that D divides 75. And also, from this first equation, so let's say this is from star star. From the first version of the equation, from star, we see that any common divisor of 75 and 90 also divides 525. Because here's 525 as a linear combination of 90 and 75. So if you have any common divisor of 90 and 75, it must also be a divisor of 525. So what these two things establish for us is greatest common divisor of 525 and 90 has to be a divisor of 75. Secondly, every common divisor of 90 and 75 has to be also a divisor of 525. So this gives us the result. This is the key step. This is the key observation. Key observation behind the proof, behind the operation of the Euclidean algorithm. The greatest common divisor of this pair, 525 and 90, must be the same as the greatest common divisor of 90 and 75. Yeah.
Where it says also from we see, what's that word?
Also from star we see that. It should be that, but it somehow came. I think it's a mixture of that and any. I was already thinking of any. Too fast for myself. We see that any common divisor, 75 and 90, also divides 525. So this is very interesting because we set out at the beginning to try and find this greatest common divisor. By doing an integer division with remainder, which is very easy to do for the computer, it's you just keep subtracting 90s from 525 until you can't do it anymore, and you have your small remainder. So it's a very quick operation for the computer to do. Much quicker than searching for the full prime factorization of the number. Okay. So that's an easy operation, but what you get out of it is the greatest common divisor you're trying to find is equal to this greatest common divisor. Now, which of these two, to find this or to find this, which looks easier? The left hand, if I told you to find the left-hand side, or I told you to find the right-hand side, just as problems, which one looks easier? Right side. Why? Smaller numbers, exactly. The inputs are smaller, less possibilities to test. In general, problems with small numbers are easier than problems with large numbers, okay? And that's the absolute correct observation. This one is easier. How did we get to this one? We got to that one by doing this integer division, by dividing the larger number in our problem by the smaller one and finding the small remainder. And then we're saying the greatest common divisor of 525 and 90 is equal to the greatest common divisor of 90 and 75. So why stop there? Why not keep going? We say 90, now we'll divide 90 by 75. Well, it's 1 times 75, put the 1 in, plus the remainder of what? 15. Now we get an easier problem. We observe that the greatest common divisor of 90 and 75, by the same explanation as before, it's now equal to the greatest common divisor of 75 and 15. So our original problem now, we've now reduced it an awful lot. It's now equivalent to a problem with smaller numbers still.
The aim to get it as small as possible.
Genius statement from the front here from Sukesh. The aim to get it as small as possible, yes. How small can they go?
Prime numbers.
How small can these numbers go?
5, 13, 15.
Yeah, but even, I mean, what's the absolute ground limit that they can get to?
5, 13, and 3. What, you mean?
More
what,
in general, not these particular numbers. Will we bounce into the negative numbers, will we? No. Because we're just dealing with these small remainders that come from the integer division process. These remainders are always non-negative. So is this process going to end?
Yeah.
Yeah, it'll, because I'll hit 0 eventually. Because the numbers are getting strictly smaller, because I'm taking the remainders from the integer divisions, kicking out the larger number, and then bringing in the remainder. But keep going.
0 anyway.
Sorry?
You can't use 0 or 1.
0 and 1 can be remainders. Yeah, let's keep going and find out.
No, there's 0 and no remainder.
Yeah, but we will reach a remainder of 0 eventually.
Oh, which means it's finished.
Exactly. I should just get Sukesh up here to Good. Well, this is the point. We need to. Sorry, I want to divide 75 by 15. I have to look to my notes because that's. Oh, that's a neat. Well, here we go. $75 is 5 times 15. That's 0. So I thought I was going to go on for a few more steps, but it's not. So what do we say? We say the greatest common divisor of 75 and 15, which is equivalent to our original problem, because it's equal to this, and that's equal to that. The exact same analysis applies. It's equal to the greatest common divisor of 15 and 0. Now somebody tell me what that is equal to.
3 and 5.
Let yourself down, Sukesh. I called you a genius before. Don't prove me wrong.
What equivalent of?
No, what's it equal to? What's the greatest common divisor of 15 and 0? 15 or 0?
Wait.
15. 15 divides into both.
15 divides into both.
15 will divide into 0. How does that work? Am I genius again?
No.
Yeah, I don't divide into 0, does it?
15 divides into 0. But
Yeah, it's all that philosophy shit, how you can't divide stuff into 0 or 4.
no, it's the other way around.
What did I do? When we did properties of divisibility,
Ah, shit, yeah, tube. That's his philosophy, that don't make sense, that sentence is a bit simple.
right, okay. When we did the properties of divisibility, I did flag up. I did say the issue of 0, the status of 0 in divisibility can trip people up. Theorem 2.1, this is the properties of 0. It says everything divides 0.
What page is that?
7. Everything divides 0. 0 is divisible by everything. In particular, 15. 15 divides 0. Does 15 divide itself? Yeah. So everything divides 0. What's the largest number that divides 15? 15 itself. So the greatest common divisor is 15.
Read the page of the sentence.
Yeah. So this process of integer divisions, you keep finding small remainders, you kick out the larger pair, bring in the remainder, keep going. Eventually, because the remainders are getting strictly smaller each time, they're bounded below by 0, so eventually one of them will be 0. So eventually you'll reach a stage where your original problem has been reduced to the greatest common divisor of something non-zero and 0. For all x that is not 0, the greatest common divisor of x and 0 is x. Or let's say absolute value of x to let x be a negative number. The greatest common divisor of anything positive and 0 is just the x. Yeah. So that, in a nutshell, is the process of the Euclidean algorithm. You're presented with an original find the greatest common divisor problem, pass through integer divisions with remainder. Each time you get a remainder, you kick out the larger of the pair, bring in the remainder, and replace it with the remainder. You then do the next integer division, divide the previous number by the new remainder, get a new remainder. And from each equation, from each integer division, that links the greatest common divisors. 525 and 90 equal to the GCD of 1975. The next equation gives you GCD of 1975 equals GCD of 75 and 15. So you're stepping down all the time. Eventually you reach GCD of 15 and 0, which is automatically equal to 15. And that's the solution to the original, the greatest common divisor. So we see that GCD of, what was it, 525 and 90. Now I also said the Euclidean algorithm can produce for us the linear combinations. So let's just recap. If we recap here, it's helpful just to see them. And this is written in the notes. 5 times 90 plus 75. 90 is 75 plus 15. 75 is 5 plus 15. So the greatest common divisor is always the last non-zero remainder in these divisions. The last non-zero remainder. The sequence of integer divisions. That's the output from the algorithm. The algorithm performs these integer divisions, and whatever the final non-zero remainder is, that's the GCD of the original pair. But then secondly, can find the coefficients. You see, the theorem we proved the last time said you can always write the greatest common divisor as a linear combination of the two numbers. So the greatest common divisor of 5, 2, 5, and 90, you should be able to write it as a linear combination.
Did that say sequence?
Sequence, yeah. Sequence of integer divisions, just list of integer divisions. So the problem now is fill in these blanks, find these coefficients. And you get them from working backwards through the equations. This is the Euclidean algorithm equations. So you get the coefficients from the Euclidean algorithm equations. Now this example, because it's only got 3, it may be the next example with more would be better to look at. But you see, from one of those equations, I get 15 as a linear combination of 90 and 75. So it's 90 minus 75. So I've got a coefficient of 1 and minus 1. So that's the greatest common divisor as a linear combination of these two. But I want as a linear combination of the original pair. Then if you look at the next equation up, the next equation tells you how to replace 75 as a linear combination of 5, 2, 5, and 90. So instead of 75, I take the linear combination I get from the next equation up, which would be 5, 2, 5 minus 5 times 90. And then collecting coefficients, I've got 6 times 90 minus 1 times 5, 2, 5. So that's 15. So by working backwards through the Euclidean algorithm equations, you get coefficients that give you the greatest common divisor as a linear combination of the two numbers.
That's the get coefficients from example 4.
Get coefficients from the Euclidean algorithm equations. I've just labeled these the Euclidean algorithm.
What does Euclidean mean?
Well, it's named after Euclid.
Oh,
famous Greek mathematician. Yeah. So the Euclidean algorithm, his algorithm. Okay, so let's look in the notes at a slightly longer example. Let's see it operating. We'll save time by not. It's a bit painful to watch me do arithmetic on the board, so it's better to look at the recorded version. So if you go over the page, let's look at this example.
Sorry, do you mind moving up to the side? Thank you.
So if you look to example 2.3 over the page, you see there we have to find the greatest common divisor of 12,378 and 3,054. Okay, so kind of very large numbers, so very hard problem. And we'll assume that those numbers are too large to go and try and find the prime factorizations of. Okay, so we want a method to find their greatest common divisor that doesn't rely on that. Okay. So you can see, so 12,378 and 3,054. So we do the integer division. We get a smaller number, a remainder. It's going to be smaller because it's smaller than the 3,054. It's the small positive remainder that's left behind. Then you just do the next division. So now we're dealing with the pair 3,054 and 162. Do the integer division, small remainder 138. This is now the pair 162, 138, remainder 24. 138, 24, remainder 18. 24 is 1 times 18 plus 6. Now we've got 18 and 6, and we get perfect divisibility. 18 is 3 times 6. That's our remainder of 0, so the process stops. And this thing sitting here, the last non-zero remainder, that's the greatest common divisor of the two numbers at the beginning. GCD of 12378 and 3050. It has to be because the way the pairings go. The greatest common divisor of this pair is equal to the greatest common divisor of this pair, is equal to the GCD of this pair, this pair, this pair, this pair. And what's the GCD of this pair? 18 and 6. Well, 6 divides itself, 6. And this equation shows us that 6 divides 18, because it's a remainder of 0. This last non-zero remainder, that's the GCD. Then we would search for, we would also like to obtain the linear combination of the original two numbers, 12,378, 3,054. The linear combination of those two, that gives you 6. But from the second last equation, you get a linear combination of 6, not of the original pair, but of the last pair, 24 and 18, or the second last pair, 24 and 18. Then if you look at the next equation up, the next equation up will allow you to substitute for the 18. Because these numbers here always have a coefficient of 1, because they're the remainders. So this equation up here allows you to express 18 as a combination of 138 and 24. So you see them. Now when you're doing this in the examples for yourselves, what you don't do is evaluate any of these products or sums. Because you don't want to, we already know it evaluates to 6. But you want to remember what you're doing is you're trying to find coefficients in this final linear combination. So you just want to collect terms. Don't go evaluate, don't say 5 times 24 is 120 or something. That's not what we're interested in. We're interested in keeping the 24s. So you replace the 18 with 138 minus 5 times 24. You collect together coefficients. So we've got 6 24s minus 138. Then you replace the 138. You can do that with the next equation. 138 is a combination of 3,054 and 162. So I've got 6 is 24. So sorry, I'm not replacing the 138 yet. Sorry, I skipped over myself. Here I'm replacing the 24. You always replace the smaller than them. So sorry, I skipped myself. Here we see 24 is a combination of 162 and 138. So we use that combination to get rid of 24, then collect together coefficients. Now we've got 6 as a linear combination of 162 and 138. So we're moving up the pairings all the time. You just keep going. Keep replacing, collecting, replacing, collecting. Eventually, you replace the 162 with 1, 2, 3, 7, 8, and 3, 0, 5, 4, and you'll collect the terms and you'll get your final linear combination. Okay? So you get these coefficients 1, 3, 2, and minus 5, 3, 5. Those are the coefficients for the GCD of the original pair. So in the notes you will see we have formal proofs of these things. But really, it is formal proofs there, but it's really nothing extra than the issues we've just discussed with those examples. So we'll just look briefly at the formal proofs. So the first of all, we have a lemma 2.4. Lemma 2.4 just examines a single integer division with remainder. and it proves that the GCD of AB, the first pair, is the same as the GCD of B and R. Okay, obviously, the principle we were using. Sorry, I jumped straight into the example then. Do I prove that lemma or? Okay, we'll do it. Maybe we need to prove that on paper. So lemma 2.4. Well, I mean, it's really just repeating the same argument I had before, but now just using letters rather than numbers. So we've got an integer division with remainder. Of course, it's equivalent to this equation. Moving one thing over to the other side. And then applying theorem 2.1 part 3. So what does that mean? What did that say? If you look back at it, that says if you've got a common divisor of two numbers, that common divisor also divides any linear combination of the two numbers. So we see two things. Any common divisor of B and R divides A, and also any common divisor of A and B divides R. Because here we have A as a linear combination of B and R. So anything dividing B and R must divide A by R. Thing we proved last week or the week before. And the second equation, any common divisor of A and B must divide R, because R is a linear combination. So that means the pair AB have the same common divisors as the pair BR. BR is a smaller pair. Okay. B is the same in both cases, but the R that comes out is going to be much smaller than the A. Smaller than the A. So in particular, so they've got exactly the same common divisors, so in particular, their greatest common divisors are the same. So that's just exactly the same argument we talked to with the 525 and the 90 and the 75, but just saying it in general. That's the nicest kind of proof, the proof that just really just follows any particular example. Of course, not all proofs are like that. But so is that okay? Any questions about that or clarifications on that? So do notice as well that, you know, as with all of mathematics, this course it's all each result builds on previous results. So we're calling back to a previous result there. That any common divisor of a pair of numbers also divides any linear combination. Okay. Yeah.
You know how like number theory and cryptography point to the same module? How's it interlinked to each other? How's it
interlinked? Yeah, well the link comes through the properties of prime numbers and the properties of congruence arithmetic, modulo arithmetic. So you really see it come to fore in term 2 when you're doing the public key cryptography.
Modern
cryptography, yeah, that relies for its security and the way it can operate, the public key aspect of it, on properties of the integers related to prime factorizations and related to congruence arithmetic and other kind of number theoretic ideas. Yeah. And it's extremely powerful. I mean, I'm sure John has talked a little bit about it in his introduction, but I mean, it's worth just taking a minute, because it's kind of paradoxical, right?
What's paradox?
Paradox is something which seems contradictory or seems like it can't be true, but nevertheless is true. And what's paradoxical is, if I want to, is that Nicholas with his head in his hands in the back row? Right. Nicholas, yeah. Right now, I'm just trying to get the names. Supposing I wanted to start communicating secretly with Nicholas, right? And I don't want you guys to know what we're talking about. But the problem is, you're sitting here, so you can hear everything we're saying to each other, right? Sorry? Text.
Oh, you mean like
we're speaking with analogies here. But if I text, the phone networks can see the text, and the government spies can see what the text is. If I want to communicate secretly with Nicholas, but you're all here listening, the public key cryptography enables me to do that. I can start exchanging messages with him, and we can set up a protocol, which you'll be learning about in term 2. And it's to do with agreeing on how we're going to communicate, agreeing on how we're going to encode our message into numbers. And then we'll talk about the modular arithmetic we're going to use. And I don't care that everybody hears all our setup exchanges. We can pass our setup exchanges from one person to the other. I don't care if anybody else hears them, but we can set things up in such a way we can then start communicating secretly. And you can still hear all our messages, but none of you will know what we're talking about, because you're able to set up a shared secret in full hearing of everybody else. And that's what seems paradoxical. Because I could have, before the class, I could have agreed with Nicholas, all right, here's the secret code we're going to use, and only you and me know it. And then I'll start using it in the class, and then the rest of the class won't know, right? But that's insecure, you know, because if we set up the secret code and we wrote down all the instructions, maybe that could have leaked out, or maybe someone else could have gotten a hold of those instructions. So it's the paradoxical ability to agree the setup for the code in full hearing of everybody, but even though everybody has heard all the exchanges we've made, they still can't crack the code, because it relies on, well, it's this weird kind of paradoxical thing that we can settle on an agreed secret without both of us knowing the complete details of the secret. It seems impossible, paradoxical, but yet it is true.
Now what, banking?
Well, so these principles underlie all the secure communication on the internet. Because the thing, when you're sitting at home doing your banking, you don't know, and you can't guarantee the route that the signals are taking. For all you know, the internet communication between your computer and the bank, it could be passing through, well, to repeat the propaganda, it could be passing through Russia. Russia's the big enemy, but no, probably not. But the point is, you don't know where the signal is traveling. But nevertheless, you can be confident that those communication with yourself and the bank is secure because of this principle of public key cryptography. So even though none of the exchanges, none of the data you exchange, you know, the actual communication down the line between you and the bank, you have to assume that anybody could intercept that. But yet, the principles of public key cryptography allow the encryption to happen on your computer and the decryption to happen on the bank's computer, but without you setting up an agreed secret beforehand in secret from everyone else. Yeah. Okay. Probably spent a few more longer minutes on that. So that's all to come in term 2, public key cryptography. Lemma 2.4 we've just proved. So that sets us up for looking at, you know, how we prove the Euclidean algorithm. But the proof of the Euclidean algorithm, it really is just the same as the examples we've looked at, except, of course, it's all letters, no numbers. So we set out the task of finding the GCD of A and B. We've seen that A is the larger of the two numbers. So we want to find the greatest common divisor, and we want to obtain the linear combination. Well, we just imagine the integer divisions with remainder. You divide a by b, and you get a small remainder. The remainder is strictly less than b. I'm assuming they're both, a and b are both positive numbers. You then divide b by r1. You get a new remainder r2. And r2 is strictly less than r1. Because you've been dividing by r1. So the remainder you get is smaller than it. Then you divide r1 by r2. Then you divide r2 by r3. Then you divide r3 by r4. So on. Okay? So you keep performing the integer divisions with remainder. Eventually you'll reach some point where you don't get a remainder. You get a clean, perfect divisibility. So you'll reach a point where the remainder Rn minus 1 will be actually divisible by Rn. The remainder is 0. And this last non-zero remainder, that has to be the greatest common divisor. Okay? So this is all still the statement, but it kind of proves itself. Okay? And the reason that's the greatest common divisor is we know each integer division links the greatest common divisor of the preceding pair with the next pair. And what's the greatest common divisor of these two? Rn minus 1 and Rn has to be Rn. Because Rn divides itself. The equation says that Rn divides Rn minus 1. The greatest common divisor of each pair is equal, and we can observe the greatest common divisor of the final pair is equal to Rn. That's really all there is to the proof. And then just describing the backward substitution process. So you start at the bottom, the second last equation there, or the last equation, you don't go to that one. And that one allows you to express the GCD, which is Rn, as a linear combination of Rn minus 2 and Rn minus 1. Then you look at it's not written there, but you look at the next equation up, so which isn't shown here. But the next equation up expresses Rn minus 3 as a linear combination of Rn minus 2 and Rn minus 1. So that's going to allow you to replace the Rn minus 1 with Rn minus 2 and Rn minus 3.
What are Q1, Q2, Q3?
Those are the quotients appearing. So we don't... Yes, this is A is Q1 times B plus R1. So just like in our... So the Q's are like... So the Q's are the 4, the 18, the 1, the 5, and the 1, and the 3. Yeah? So we kind of discard them at each stage. We're just dealing with we take the B and the remainder. B and the remainder. B and the remainder. Those are the ones we do. Of course, they come back into it because when you're doing the back substitution phase, you need to use those numbers. So you keep doing the back substitution, and eventually you'll get Rn as a linear combination of A and B. Substituting all the way back up through the equations. Okay. So that leaves us with a huge bunch of exercises. I've only got 5 minutes left now, but in the tutorials next week, and maybe in one of my lectures next week, we've got an awful lot of exercises to look at. So back before the Euclidean algorithm stuff, we have this set of exercises here. So there are exercises on using the idea of the greatest common divisor, co-prime. And then after the Euclidean algorithm there, you've got some more kind of practical calculation type examples. Just doing the Euclidean algorithm for a bunch of examples. And then some further end of chapter exercises then on divisibility and the greatest common divisor. There's a whole bunch of questions. There's more questions than we can fit into any particular tutorial. So do start working on those, and we'll do some intensive work with those in next week's tutorial. There's a few other little results there in chapter 2, but I'll leave you to read through those yourself, and we'll have a look at them next week as well before we move on to chapter 3. Okay. So, quotient. Quotient, I just mean, so yeah, I referred to, when you do a division like this, A equals Q times B plus the remainder R, you can call the Q the quotient. Yeah, it's the amount of times B goes into the A. So you're dividing this by this, and the parts of the division are the quotient and the remainder.
How come the quotient was
Well, quotient also, you can also use it to refer to a fraction. It's one thing divided by another. Yeah, I'm using it for slightly different things, but so you've got in this integer division, you've got the quotient of the remainder. In an integer division like this, dividing 12,000 by 3,000, so the parts of the division are the quotient 4 and the remainder 162. This is, that's the divisor, that's the divisee. If you want to name everything like that. Yes, that's the divisee, that's the divisor. This is the thing you're dividing, that's the thing you're dividing by. The thing you're dividing by is the divisor,